Suppose we have a company and our company is advertising a product, and the advertising is expected to improve the net profit of the organization. Now, the advertising costs some money, and initially when just a very little bit of money is put into advertising, it doesn't really draw very many people to our product, and it only detracts from the profit of the business. But as more and more money is put into advertising, it draws more and more people to the product within our business, and the net profits begin to increase. And a graph of the situation might look something like this. If we have the advertising dollars along a horizontal axis and net profit along the vertical axis, then maybe we start our advertising with these many dollars right through this region of the graph, and the net profit of the business tends to sort of drop at first because the advertising dollars are pulling from that net profit. But as people are drawn to our business, then the advertising dollars start to pay off, and then the profits begin to soar. But eventually we're spending so much money on advertising that it's not really panning out profit-wise, that we actually start to level off on the profit, that there's sort of a maximum amount, not exactly a maximum, but sort of an area where the returns on that profit start to diminish. Well, let's see, let's put that in the perspective of slope. And what we're talking about here for points on this graph would be, well, let's see, we're talking profit per advertising dollar. So the slope here is sort of a rate having to do with profit per ad dollar. You see, here we have a profit per ad dollar at that point, and profit per ad dollar at this point, and so on. And it's kind of the rate at which our advertising dollars are bringing in profits to the company. Now, that rate is decreasing through here, and that rate begins to level off here, and then that rate begins to improve. Now, if I were the manager of this situation, then I would want to know that exact point. Now notice the slope here as I go through. The slope number is getting larger and larger because the slope is becoming more and more steep through here. Then at some point, that slope begins to diminish. That slope starts to go down just a little bit. Now, what that means in terms of advertising profit and the profit per ad dollar is that the profit per ad dollar starts to diminish through here, that we're not getting the returns on that ad dollar that we got over here. So if I were a manager in this, I would want to know exactly where that profit per ad dollar rate began to decrease. I would want to know this place where the graph stopped doing this and began to do this. Now, this kind of behavior of the graph is called concave upward, and this behavior is called concave downward. And that's one of the things we want to examine in this segment. Another thing we'd like to be able to do is to identify this exact point where we go from concave up to concave down. That's called a point of inflection. And it turns out that it's not difficult to identify. It's pretty easy to identify. Let's take a rather exaggerated situation of concave up and down. Here we have a graph that's concave up very distinctly through this area of the graph, and then concave down through here. Now, I'd like to talk about this in terms of slope, obviously, and then we're going to overlay the derivative function, the graph of the derivative function, right on top of this, and see some of the behaviors involved with that. Now, we already know some things about what to expect here with the first derivative idea because of our first derivative test earlier. But think about now, if I am going to construct the graph of the first derivative, then I know that that graph will have zeros at the relative maximum and minimum points on the graph of f. So this is f. Now here's a relative minimum, so I'm going to have a 0 of my f prime function right here. Here is a maximum, so I'm going to have a 0 of my f prime function here. Now, think about values on the f prime function through this region of the graph. Now, notice that I have a downward sloping graph of f. So it means that the slope of the tangent line here is negative, and that means that f prime is negative through this region. So f prime is somewhere down here and is coming up to that point in this interval of the graph. Okay, so let me just put a point down here just to indicate where we are in this interval. Now, in this interval, what's going on? Well, I've got an increasing graph, and so all of the values are positive for f prime. Positive slope, you see, all through here. Now, what about the change, though, in that positive slope? You see, the slope has small positive numbers here, larger, larger, larger positive value, large positive value, but then it has a largest positive value in here, and then it begins to get a little smaller positively, still positive, but a little smaller number, and then smaller, smaller, smaller down to 0 right here. So we have kind of a maximum positive value right in this neighborhood. And let's identify that, let's say right here. Let's say that that point of inflection is here, and we have a maximum point on the graph of f prime at that place. All right, then, so what's happening is the graph comes up here, and it's going to hit that maximum point and go back down to this point. And then on this side, in this interval, let's see, the expectation is that we have negative values for the slope, and so negative values for f prime would put us below the x-axis, and so we have points that go out this way. So the graph then of f prime looks like this. And lo and behold, the inflection point happens to be at the maximum point on the f prime graph. Now, think about that, but how do we identify that exact spot? How do we identify the exact highest point here on f prime? So we have f here, we have f prime here. Well, you know, this is a function, and if it is a function, then we can identify a maximum on this function by taking its derivative. You see, the 0 of its derivative would give us a relative maximum or minimum point on its graph. Now, the derivative of f prime would be f double prime. It would be the second derivative of the f function. Now, let's think about the graph of f double prime, but don't think of it in terms of a relationship, or let's not refer back all the way to f. Let's just think of the relationship between f prime and f double prime. All right, so the derivative function of f prime, how will it behave in different regions of the coordinate plane? Well, let's see. Through here, the derivative of f prime, let's see, we have a slope that's positive through here, and in fact, all the way through the interval to this point, we have a positive value for f double prime. So the values of f double prime are up here. Now here, when the slope becomes 0, we have a 0 for f double prime. So the 0 then would be right here. And so we're coming from positive values for f double prime down to here, and then we go into negative values. So f double prime has this kind of behavior. All right, so the 0 then, because it's the 0, this 0 corresponds with a slope of 0 on f prime. The 0 of f double prime identifies that point of inflection. That's a very important idea of what we're going to discuss. Another idea that we need to discuss further is this, that notice that on the interval from this 0 of f prime on the interval to the left of that 0, in the region where f double prime is all positive. Notice what's happening in the original graph, in the graph of f, that in this interval, all f is entirely concave upward. And then the interval where f double prime is negative, you see all the values of f double prime lie down here, then our original function turns out to be concave downward. And all of those aspects are coming into play here. We want to be able to talk about concave upward and downward, and we want to be able to identify inflection points. Take a look at this function. 1/4 x to the 4th minus 2x squared. We want to analyze this in terms of regions where we have a concave up or down situation, and we would also like to identify relative maximum and minimum points and also points of inflection. The first derivative is x cubed minus 4x, and I'm finding the zeros of this function. Turns out that the zeros are 0, -2, and 2. Okay, so these are the zeros of the first derivative. That means that these are candidates as points that are relative maximums or relative minimums. All right, second derivative. Second derivative of the function is this, and these are the zeros of the second derivative. And just to give a feeling for what this 2 over the square root of 3 is all about, it's approximately 1.15. So we have zeros at plus or minus 1.15, roughly. Now, we can think about subdividing our graph into intervals that are determined by this value, these values. And those intervals would be from negative infinity to -2 the square root of 3. And then between those 2 points, -2 over root 3 to 2 over root 3. And then another interval 2 over root 3 to infinity. All right, now, we want to examine the behavior of the second derivative in those intervals. So we choose a point in the intervals, we pop that x value into our function, and we determine whether the function is positive or negative throughout the interval. Okay, in this interval it turns out that the second derivative function is positive, and in this interval negative, and in this interval positive. And as we discussed earlier, that if we have an interval over which the second derivative function is positive, we have a graph of the original function that is concave up. So the original function is concave up in this region. Now here the function is negative, so the original graph is concave down. Here the function is positive, so we have again concave up. Now we can examine the situation about relative maximum and minimum points in a couple of ways. One way is like this. We can say, well, we have points that are candidates as maximums or minimums. These are those 3 points. Now let's just see what intervals these fall into. You see, if they fall distinctly into one of those intervals, then we're bound to have a maximum or minimum point. And as a matter of fact, if a candidate for max or min falls into an interval where we have concave up, then that point must be a relative minimum. If one of those candidate points falls into a region distinctly in a region where we have concave down, then the point is a relative maximum. And truly, that's all there is to it. So let's see, what about 0? What region does 0 fall into? Well, let's come over here. Oh, 0 is in the interval from -2 over root 3 to 2 over root 3. So 0 is distinctly within an interval where we're concave down. If we're concave down and 0 falls in there, then 0 must be a max. So let's come back over here and label this 0 as a maximum point, relative maximum point. And -2 and 2 fall into the other regions. Both of those other regions happen to be concave up, and they fall distinctly within those regions, so those other 2 points are relative minimums. So we're talking about minimum. Now, okay, so that's the long story about how to determine these as relative maximums or minimums. There's kind of a shorter way to do it. If it turns out that all of the values of x give function values that are positive within this interval, you see, and a distinctly negative situation in this interval, positive within this interval, rather than finding the intervals and going through this whole process and determining concave up and concave down beforehand. We could do this. We could just take those candidate points, the 0, -2, and 2, and just pop them into our original function. That is, now we know that if these are inflection points, then they kind of subdivide our graph into concave up and down regions. All right, we kind of know that. Now, where do these points 0, 2, -2 fall? And what about concave up or down? Well, let's see. -2 would fall in, if we're thinking intervals, and would fall into the region to the left. So what about examining f double prime of -2? You see, what is this? What is the value here of f prime negative? Well, let's see, -2 squared, that's 4. 12 minus 4, that's 8. So this turns out to be 8, which means that it's positive, which means that it's in an interval over which all of the values are positive, which means that if all of the values in the interval are positive, then that means that, you see, we're concave up. This guy is a minimum. You see, all we have to do is determine positiveness or negativeness of f prime of the zeros of, or f double prime of the zeros of f prime. You see, and that's really all we have to do. So we determine here, because this is positive, that x equals -2 is a minimum, relative minimum. All right, and in a similar way, we examine the others. For 0, okay, let's do the test. We would say, oh, well, let's see, f double prime of 0. Well, what's that? Pop 0 into that, and we get -4. So since it is negative, you see, I don't care if it's -1, -4, -10,000, it's negative, and that's what tells me that this is a region where all of the values are going to be negative, where we have a concave down situation where this point is going to be a relative max. So it implies that x equals 0 is a max. So that's the idea. We don't have to go through the interval examination. If we don't want to, we can simply find f double prime of the zeros of f prime, you see, to make this determination of minimum and maximum. And the zeros of f double prime are the inflection points. Well, a look at the graph would show this to be the case. That is, if we were looking at the graph of the f function, we would see that we have a maximum point at 0, we have a minimum at -2, another minimum at 2, and we have inflection points at, just over 1 and just below -1. Well, to summarize this, what we've just found, we entered the second derivative test. Let f prime of c be 0. So c is a 0, you see, of the f prime function. If f double prime of that 0 of the first derivative function is positive, then f of c is a relative minimum. If f double prime of c, that 0 of the first derivative function, is less than 0, if it's negative, then f of c is a relative maximum. And if f double prime of c turns out to be 0, then all bets are off. Then the test fails and we have to analyze it in another way. Well, let's consider this other function right quick. Here's one. This one has a rather interesting twist to it. F of x is this. F prime of x is this. And these are the zeros of that. These are the zeros of the first derivative. So these are candidates as maximum and minimum points. All right, good. Here's f double prime of x. And these are the zeros of f double prime of x. I want to show the zeros because these give us the inflection points. I want you to notice that we have an inflection point here and we have a candidate as maximum or minimum. And you put those two ideas together Well, let's see what happens with our test, our second derivative test. Now, I've set up intervals here just for convenience, just to pop them into the, I think it may be a little easier to see if we have the intervals, but from negative infinity to 0, from 0 to 2, and from 2 to infinity. All right, and the second derivative is positive in this interval, negative in this one, and positive in this one. So we have an up, down, up situation. Now, where do these points fall? Well, 0 falls at the edge of, you see, not distinctly in either of these two intervals. So for 0, the test sort of fails. F double prime of 0 is 0, and that's why this test fails over here for our second derivative test. Now, F double prime of 3 would fall into, let's see, this interval. F double prime of 3 turns out to be positive. We wouldn't need all of this interval information. Since 3 falls into the interval and we're concave up, we know we have a relative minimum. So we have a relative minimum at that point, but we would know it just by taking F double prime of 3 to be positive, and we know we have a minimum there. Let's take a look at this one on the graphing calculator. We talked about several ideas sort of algebraically. Now we'd like to look at them graphically. Here's a graph of the original function, and notice that the function flattens at this point and we have a relative minimum here. One of the important notions about the second derivative is that the zeros of the second derivative will give us inflection points in the original graph. The zeros of f double prime were at 0 and 2. Now these are inflection points on the original graph, and that means that we have this concave up, concave down situation changing at these points. Here the graph is concave up along this interval from negative infinity to 0, and in between these two zeros of f double prime we have concave down, and then from this point on to infinity we have a concave up situation. Let's bring on the other graphs and talk about some other ideas. Remember, now you may recall that this same graph, we had a very similar graph when we were talking about the first derivative test earlier. I'm just going to bring on the graph of f prime, and we want to look at the zeros of this graph. The zeros are at 0 and at 3, and these are the candidates for relative maximum and minimum points. Now, with our second derivative test, we have a way of telling whether or not we do indeed have maximums or minimums at these points. We just take f double prime at these points, and if f double prime is distinctly positive or negative, then we do have a hit on a maximum or a minimum. If f double prime is not distinctly positive or negative, then we do not have a hit. Now, we won't have a hit right here. That is, we will not have f double prime being distinctly positive or negative. And no wonder the graph flattens at this point, and no wonder we have a 0 for f prime. You see, if the graph flattens, the slope is 0, and so we have a 0 of f prime. But that, in this case, doesn't imply a relative minimum or maximum point. Let's bring on f double prime. I'm selecting it now, and I've constructed its graph in a dotted line. Notice that the zeros are at 0 and 2, as we mentioned before, and now we're looking to see if this graph is distinctly positive. That is, if f double prime of 0 is distinctly positive or negative, and f double prime of 0 is 0. And so that's why we don't have a relative max or min at this point. On the other hand, the 0 of f prime, it was at 3, and f double prime of 3 turns out to be distinctly positive, and therefore we have a relative minimum at that point.